to move on to our keynote addresses, but just like the ESnet6 project, we're a little ahead of schedule. So I'm going to do a quick check with our folks to make sure that are our speakers ready to go? Thumbs up. Okay. I'm going to start the introduction and we'll see what happens. So because we're really excited to get to our keynote addresses this morning. I'm really honored to introduce our keynote speaker, Dr. Vint Cerf, Google's Vice President and Chief Internet Evangelist. He is a true luminary. Referred to widely as the father of the internet, Vint co-designed TCP/IP, the foundational communication protocols that define the architecture of the modern day internet. Vint serves as a key advisor to a wide range of organizations, including DOE's Advanced Scientific Computing Advisory Committee, or ASCAC. He's the recipient of numerous prestigious awards for his legendary work, which have had unparalleled global impact. Notably, he has received the U.S. Presidential Medal of Freedom and the ACM Turing Award, among many, many, many other accolades. Please join me in welcoming Vint Cerf.
Well, good morning, everyone. I hope I'm audible. Can I get indications that you can all hear me? Hearing nothing, says the deaf guy. He's hoping that everything is working properly. At least I'm unmuted, if nothing else. First of all, I'm in New York right now, so I wish I could be there with you personally, but it's the best we can do. And thanks to this technology, it's possible for us to participate remotely. I was very pleased to see that Senator Padilla and Representative Lee were able to participate in this opening of ESnet6. This is an astonishing accomplishment, but it's simply one of many that DOE and the ESnet team can claim. Some of you will know that DOE was among the first of the agencies in the research supporting agencies in the US government to adopt and implement the internet protocols after the ARPANET was built starting in 1969, and the internet was introduced in 1983 with the original three networks, the packet radio net, the packet satellite net, and the ARPANET. DOE recognized the need for and the utility of networking well before that, and they had already implemented the high-performance physics network. But they adopted the TCP/IP protocols as part of their initiative to move forward into a highly collaborative environment. And they were joined, interestingly and nearly concurrently, by the National Science Foundation and by NASA. With the NASA Science Internet and the NSFNet backbones. Together with ARPANET, ESnet, those four networks became the core backbone of the American internet, certainly in the research and academic community. And thanks to ESnet's efforts, we learned many, many lessons about what the academic and the scientific computing community needed in the way of resources and access and the ability to move information around among the various supercomputers. One of the motivations behind the internet design was indeed to connect a large range of users in the research community, several thousand campuses, to access to high-speed computing resources such as those that NSF and DOE jointly produced. So we learned quite a bit from that experience in ESnet's effort to support the users of that system. And you have just an amazing track record of high speed and capacity that ESnet 1, 2, 3, and so on have continued to produce. At this point, however, ESnet6 is really, in my opinion, a turning point in design and architecture. It has the capability to do much more refined resource allocation and the, I would say, the configuration of its resources to support unusual, either very high speed or certain timely demands, the ability to adapt quickly at need. And that, I think, is an additional capability that the previous versions of ESnet have not had in nearly the same degree of flexibility. I have to say that this particular ESnet team has kept up with and in many cases pushed the envelope of commercially available resources. I can say at Google that we share this zeal for high speed. We're both looking at the 400 gigabit per second optical fiber capabilities per channel, and I know that we're both looking forward to 800 gigabits per second per optical channel when that equipment becomes more available. So all this tells you is that the ESnet team is absolutely at the forefront of networking capability and flexibility. So this is the thing that I find frankly astonishing about ESnet6 is that Inder Monga and his team have been able to implement this system, add new fiber and repurpose older fiber, and at the same time serve all the needs that ESnet5 needed to serve and continued to serve while they were building ESnet6. And I'm sure, I hope anyway, that Inder will give you more details about how this, changing the engines while the plane is flying was accomplished, because it is no mean feat to continue to serve a demanding community while literally introducing a dramatic upgrade, not only in capacity, but also in flexible architecture and management. So the fact that they could cut over to ESnet6 essentially without much visibility at all is nothing short of astonishing. On the other hand, we shouldn't be too astonished, because Inder and his team are frankly the best you can get. And that's one of the reasons that DOE has continued to be such a leader in computer networking technology, as well as computer design and implementation for high-speed computation. The things that ESnet6 offer, at least as I see it, are some opportunities to explore terra incognita. One area of considerable interest to me and my company, of course, is cloud-based computing. And the ESnet6 actually offers an opportunity to explore what the relationship can be between the supercomputing resources that are available in the labs, for example, and the computing capabilities of cloud-based systems. The idea of interacting with the cloud-based systems as sort of intercloud capability, from my point of view, is a very important opportunity to explore how to make that work. You can just think a little bit about the challenges here. Not only do you need connectivity between the cloud systems and the ESnet6 and the supercomputers that are supported by ESnet6, but you need to think your way through, what does this look like from the user's point of view? How does the mix of supercomputers and cloud-based services look to that user? How do we make the clouds compatible with each other? So that means some standardization is required. There's a big question about access control and the control of the data that is held either in the supercomputers or in the clouds or elsewhere. The idea of having some sort of inter-cloud-wide identity and authenticity is really important, not only for access control, but also for purposes of allowing a user of the DOE resources to get access to the resources of other cloud-based systems and still use their common authentication schemes in order to identify users and what privileges that they have. And so I think ESnet6 is going to essentially force us to think about what identity is and what accounting is for individual users that will work across multiple clouds and across multiple facilities. And so being essentially coerced into solving that problem, in my opinion, is a good thing. This is like a lot of other standardization. Once it's recognized that you need this capability, it's good to have incentive to achieve the objective. So that's one aspect. The other thing that, of course, ESnet6 does is allow the various labs to share information with each other and share computing resources with each other. The thing which is particularly interesting about ESnet6, though, is its ability to dynamically allocate its resources to meet various and sundry kinds of demand, some of which have quite very high variation. In the case of large-scale data collection from an instrument of the kind that you see at SLAC or at the Large Hadron Collider, for example, you have to be able to ingest an enormous amount of data in a big hurry. But you don't always need to do that all the time, and so you need to be able to adjust and allocate the resources at need, and that's something that ESnet6 has introduced in a way that I'm sure we in the commercial community will obtain many lessons. So we are watching with great interest, and I hope participating in taking advantage of what you learn. And I'm sure you'll be willing to share that, because historically you've been a source of considerable insight into the design and implementation of systems like this. Another thing which I think is reasonably ascribed to the ESnet6 design is increased resilience in the architecture by the addition of more fiber optic links into the system, and generally the ability to steer resources around in order to either recover from failures or to adapt to demand. And these are the kinds of things that, as I see it, are important contributors to future developments that we will probably label ESnet7, whatever that turns out to be. In the meantime, it's an opportunity for those of us who are in the commercial networking space to learn from your experiences to the degree you're willing to share them, as you have in the past, and also to collaborate with you in order to find ways of adapting unique computing resources to the needs of the DOE researchers. And here I'm thinking about not only the supercomputer resources in the various laboratories, but the special purpose processing capabilities of some of the clouds, including GPU and TPU, the tensor processing units we have at Google for machine learning acceleration, and perhaps someday quantum computing. DOE and others are very much engaged in exploring the possibilities of quantum computation. And while we're nowhere close to having machines that will perform useful computations, we're certainly seeing some of the requirements that will drive the research efforts to get to those destinations. So to give you an example, it's pretty clear that in order to have a functioning quantum computer, you need to have more than one qubit, physical qubit per logical qubit in order to do error correction. Why do you have to do error correction? Well, entanglement doesn't last forever. And the problem of maintaining entanglement in order to complete a computation means that you have to cope with potentially degraded conditions over time. And that means that you want multiple error correcting physical qubits in order to make up a logical qubit. And in some cases, it could be as many as 100 or perhaps even 1,000 physical qubits to make up one logical qubit. So if you need more than one logical qubit to do a computation, and you do, then we may be talking about hundreds of thousands, if not millions, of physical qubits. We probably can't jam that many qubits into a single quantum computer. And so now we get into this question of, well, how do we build a machine of that scale when we can't build a single machine that way? And the answer, of course, is, well, let's build multiple machines and somehow tie them together. But that leads to this question of how to move entangled information in order to entangle multiple computers together, multiple quantum computers together. And that, frankly, implies the movement of entangled photons from one place to another. Many of you have heard the phrase, quantum internet, and I remember chuckling at the time, thinking, well, somebody just took the latest buzzword and stuck it on the front of internet. But the honest truth is that we do need that capability to move entangled photons between quantum computers in order to effectively entangle the computers together and build what is, in effect, a much larger quantum machine. Which means that the ESnet optical capability is going to be has to be applied to both of the problems. One of them is super high-speed conventional digital transport, But the other one is the ability to transport single entangled photons reliably and to essentially repeat them through repeaters. And I don't have to tell everybody in this audience that you don't just copy an entangled photon because the normal copying destroys the entanglement. So you have to do some very funny things called cloning, and we have to be able to do that using quantum relay systems. And so the ESnet6, in my expectation, is going to be an important avenue for exploring quantum networking in addition to the conventional networking, which it has already contributed substantially to. So if you're like me, you're going to be watching with great interest the experiences that the ESnet6 team have and share with the rest of us as they explore terra, as I say, terra incognita in the world of computing and communication. So congratulations again to the ESnet6 team on this launch, successful launch of the new networking services. Please don't stop there. We know there's more work to be done. And we know that while ESnet6 is running, that Inder and his team will be out there exploring what's at the edge of the envelope to bring us the next big thing. And I'll be around, I hope, to watch that happen as part of the Advanced Science Computing Advisory Committee. So I'll stop there with my congratulations. If I had a hat on, I'd take it off and tip my hat to you. Wish you well for the rest of this conference. I need to run off to yet another event here in New York. But congratulations again and best of luck.